If NASA decided tomorrow, right now, today, to send a new mission back to Pluto, the scientists working on that mission would very likely not live to see it arrive. Depending on exactly which rocket carried it and exactly which path it took through the solar system, a new spacecraft launched today could take anywhere from 26 to nearly 28 years just to reach Pluto, meaning a graduate student beginning their career on this mission today would be approaching retirement by the time the spacecraft actually got there. That is not an exaggeration built for dramatic effect. That is the literal, calculated travel time NASA's own scientists have already worked out in real, detailed mission planning documents. And that single, brutal fact sits at the very center of why, more than a decade after New Horizons gave humanity its first ever close-up look at Pluto, no follow-up mission has ever actually been sent. This is the real story of why NASA has not gone back to Pluto, why a genuinely serious, fully designed mission proposal already exists sitting on a shelf, and why the reasons it has not yet flown have almost nothing to do with a lack of scientific interest. To understand why this question matters at all, you first need to understand exactly what New Horizons actually accomplished, and exactly what it left unanswered. NASA's New Horizons spacecraft launched in January of 2006 and did not reach Pluto until July of 2015, a journey lasting 9.5 years just to cross the distance separating Earth from the outer edge of our solar system. When it finally arrived, it was never designed to enter orbit around Pluto at all. It was built specifically as a flyby mission, meaning it sped past the entire Pluto system at more than 30,000 miles an hour, gathering as much data as its instruments possibly could during a single brief encounter lasting only a matter of hours, before continuing onward, deeper into the Kuiper Belt, eventually conducting a second flyby of a small distant object called Arrokoth in January of 2019. New Horizons revealed a genuinely astonishing, unexpectedly complex world, towering mountains of water ice, a heart-shaped glacier of frozen nitrogen, and a thin, surprisingly structured atmosphere layered with delicate blue-tinted haze. But a flyby, by its very nature, can only ever capture a single frozen snapshot. It cannot watch how anything on Pluto actually changes over time. It cannot map the entire surface in detail, since a spacecraft moving that fast only ever gets a clear look at whichever side of the planet happens to be facing it during the brief window of closest approach. And, critically, it can never determine one of the single most scientifically important open questions New Horizons actually raised, whether Pluto might be hiding a genuine subsurface ocean of liquid water beneath its icy crust, a question that requires sustained, long-term observation from orbit, not a brief, high-speed pass. It is also worth understanding that New Horizons itself very nearly never happened at all, and that this entire pattern, ambitious Pluto missions repeatedly stalling out before they ever reach the launch pad, has a much longer history than most people realize. As far back as 1992, NASA scientists and engineers began developing an earlier concept called Pluto Fast Flyby, later renamed the Pluto Kuiper Express, once astronomers realized Pluto sat at the inner edge of a vast, newly discovered population of icy bodies called the Kuiper Belt. That mission spent nearly a decade moving through NASA's proposal and funding process, and it came remarkably close to actually flying, reaching the point of selecting scientific instruments before its projected cost climbed past $1 billion. In September of 2000, NASA's science leadership canceled the mission outright, citing its expanding budget, and for a brief period afterward, it genuinely looked as though Pluto might simply never receive a dedicated mission at all. Alan Stern, a planetary scientist who had been advocating for a Pluto mission since the late 1980s, along with allies including Planetary Society co-founder Louis Friedman and television host Bill Nye, mounted a public campaign to save the mission, gathering thousands of postcards from Planetary Society members, urging Congress to reverse NASA's decision. That pressure eventually helped persuade NASA to open a new competition for a leaner, cheaper Pluto mission, and in November of 2001, Stern's own proposal, a spacecraft that would eventually become New Horizons, was selected as the winner. Even after being selected, the mission proceeded for its first 2 years without a guaranteed budget, and its team faced a genuinely difficult scramble to meet its January 2006 launch deadline, a deadline driven by the same unforgiving orbital mechanics that govern any Pluto mission, since waiting even a few years longer would have meant either sacrificing a helpful Jupiter gravity assist or accepting a considerably longer flight time. In other words, the mission that finally did reach Pluto in 2015 only exists today because a small group of determined scientists spent more than 2 decades fighting to keep a Pluto mission alive at all, after an earlier, similarly ambitious attempt had already collapsed under its own projected costs. That history matters, because it shows this is not a new or unusual problem specific to Persephone. It is a recurring pattern that has shaped essentially every serious attempt to explore Pluto going back more than 30 years. This is precisely the gap a real, seriously studied mission concept was designed to fill. In the years following New Horizons' historic flyby, A team of planetary scientists led by Carly Howitt at the Southwest Research Institute, several of whom had actually worked directly on the original New Horizons mission, developed a detailed, fully engineered proposal for exactly this kind of follow-up mission. An orbiter that would finally circle Pluto and its moons for an extended period, rather than simply racing past. They named the mission Persephone, after the mythological wife of Pluto and queen of the underworld, and submitted it as a formal concept study for NASA's decadal survey process, the rigorous, once-per-decade planning exercise that determines which large-scale planetary science missions the agency should actually prioritize funding over the following 10 years. The Persephone concept was not a vague, aspirational sketch. It was a fully detailed engineering proposal carrying 11 separate scientific instruments, including high-resolution imagers, ultraviolet and infrared spectrometers, a mass spectrometer, sounding radar, a magnetometer, and a plasma spectrometer, specifically designed to finally answer the biggest remaining questions about the Pluto system, its internal structure, the possibility of a hidden subsurface ocean, and how its unusual haze-driven atmosphere actually evolves over time. And this is where the story runs directly into the same brutal obstacle mentioned at the very beginning. According to the detailed mission planning documents, launching on NASA's powerful Space Launch System rocket and using a gravity assist flyby of Jupiter to help accelerate its journey, Persephone would still require somewhere between 26 and 28 years just to reach Pluto, followed by roughly 3 additional years spent actually orbiting the system once it finally arrived. Carly Howitt explained the underlying orbital mechanics driving this brutal timeline directly, noting that mission planners have to wait roughly once a decade for Jupiter to align in exactly the right position to provide a useful gravitational assist, and that missing that specific launch window imposes an additional 10-year penalty on the total travel time. In practical terms, this means any realistic Pluto orbiter mission needs to launch before the early 2030s, or accept an even longer delay before ever reaching its destination. Sit with that timeline for a moment, because it is genuinely unlike almost any other active area of planetary science. A mission launched today, under the most optimistic possible planning, would not arrive at Pluto until sometime in the 2050s, and its full extended science mission, including potential encounters with additional distant Kuiper Belt objects along the way, could realistically stretch operations out past 2070, more than 50 years after the spacecraft first left Earth. Nearly every scientist who first proposes, designs, and fights for the funding of a mission like this would be retired, elderly, or in some cases no longer alive by the time it actually reaches its target and begins returning the data it was built to collect. This is a genuinely unusual burden to place on any scientific career, and it represents one of the single biggest practical obstacles standing between a fully designed, scientifically compelling mission concept and an actual funded launch. Travel time alone, though, is not the whole story, and it is worth being honest about the other major obstacle standing in the way, one that has nothing to do with distance at all and everything to do with a specific dwindling material here on Earth. Spacecraft traveling this far from the sun cannot rely on solar panels for power, since sunlight at Pluto's distance is roughly 1,500 times fainter than sunlight reaching Earth, far too weak to generate any meaningful electricity. Instead, missions to the outer solar system depend entirely on radioisotope thermoelectric generators, devices that convert the heat produced by the natural radioactive decay of a specific isotope, plutonium-238, directly into usable electricity. The United States stopped producing new plutonium-238 back in 1988. And for decades afterward, NASA's entire supply for deep space missions depended on a slowly shrinking stockpile, eventually supplemented by periodic, increasingly expensive purchases from Russia. Restarting genuine domestic production turned out to be a slow, difficult, and repeatedly underfunded process. And even today, in 2026, the Department of Energy's production rate remains constrained to a modest, carefully rationed 1.5 kilograms per year. A figure planetary scientists have publicly stated may not be sufficient to support every ambitious outer solar system mission currently being proposed and studied. This matters enormously for a mission like Persephone, because it does not exist in isolation. It is competing directly within NASA's own internal planning process against other outer solar system missions, drawing from that exact same limited supply of plutonium. And when the National Academies published their most recent decadal survey covering the years 2023 through 2032, the formal document that ranks and prioritizes exactly which large-scale planetary science missions deserve NASA's limited funding and limited plutonium supply over the coming decade, Persephone was studied seriously, included in the survey's formal appendix as a fully evaluated mission concept, but it was not selected as a priority for that decade. Instead, the survey's single highest-ranked large mission recommendation went to an entirely different target, a dedicated orbiter and atmospheric probe mission to Uranus, a world that, unlike Pluto, has never been visited by any spacecraft, except for a single brief Voyager 2 flyby back in 1986, And that carries its own set of genuinely compelling, unresolved scientific mysteries that the same panel of experts judged to be a higher immediate priority. This decision reflects something important and worth being honest about, rather than treating it as some kind of institutional failure or oversight. NASA's planetary science budget, however substantial it may sound in absolute terms, is genuinely finite, and every single dollar and every gram of available plutonium committed to one ambitious outer solar system mission is a dollar and a gram that cannot simultaneously be committed to another. The scientists who evaluated Persephone alongside the competing Uranus proposal were not dismissing Pluto as scientifically uninteresting. Multiple public statements from researchers involved in this exact planning process have explicitly stated that a return mission to Pluto remains a genuinely compelling, scientifically important goal, one that could, in the words of researchers who worked on the Persephone concept, potentially help answer profound questions about whether life might exist in a hidden ocean beneath Pluto's icy surface. The decision was, more straightforwardly, a matter of ranking one already difficult, expensive, multi-decade commitment against another equally difficult, expensive, multi-decade commitment, and choosing to prioritize whichever mission the assembled panel of experts judged to offer the greater immediate scientific return given genuinely limited shared resources. It also helps to look at exactly where NASA's outer solar system attention and funding have actually gone during this same period, because Persephone was never simply competing against a single rival proposal on paper. It was competing against missions that had already secured funding and were actively being built. NASA's Europa Clipper, a multi-billion-dollar flagship mission designed to study Jupiter's icy moon Europa and its suspected subsurface ocean, launched in October of 2024, representing one of the largest planetary science investments of the entire decade. Around that same period, NASA also committed to Dragonfly, a nuclear-powered rotorcraft mission designed to fly through the thick atmosphere of Saturn's moon Titan, sampling its surface chemistry in multiple locations, a mission whose own budget has grown to well over $3 billion. Both of these missions draw on the exact same categories of resources a Pluto orbiter would need: flagship-level funding, scarce plutonium-powered generators, and the limited pool of engineers and mission planning capacity NASA can devote to outer solar system exploration at any one time. Neither mission was selected instead of Persephone in any direct, head-to-head sense, but every dollar and every gram of plutonium already committed to Europa, Clipper, and Dragonfly is a dollar and a gram that was never available to compete for a Pluto orbiter in the first place. Seen this way, Pluto is not simply losing out to one single rival mission concept. It is one of several genuinely compelling destinations, alongside Europa, Titan, and now Uranus, all drawing from a planetary science budget that has never been large enough to fund every ambitious proposal scientists have put forward. There is also a broader, considerably less exciting reality shaping this entire situation, one that applies to essentially every serious outer solar system mission proposal currently sitting on the shelf, not just Persephone specifically. Missions to Jupiter, Saturn, Uranus, and Neptune, alongside their extraordinarily promising icy moons, all compete for the exact same limited pool of NASA funding, the exact same limited supply of plutonium-238, and the exact same limited number of major launch opportunities available across any given decade. A fully funded, fully staffed flagship mission to any one of these destinations typically costs well over $1 billion, and takes the better part of a decade simply to design, build, and test before it ever launches at all, entirely separate from however many additional decades it might then need to actually reach its destination. Given those constraints, NASA's planetary science program can realistically only pursue a small handful of truly ambitious outer solar system missions during any given 10-year planning cycle. And Pluto, despite the genuine, undeniable excitement generated by New Horizons back in 2015, has simply not yet won that specific competition against other equally compelling destinations. It is worth being clear and honest about what this actually means, and does not mean, for Pluto's long-term scientific future, rather than framing this as some kind of permanent abandonment. Persephone remains a fully studied, technically credible mission concept, sitting formally documented in NASA's own decadal survey archive, available and ready to be reconsidered, refined, and potentially prioritized in some future planning cycle whenever the balance of competing scientific priorities and available resources eventually shifts back in its favor. Nothing about the current situation suggests Pluto has been permanently written off. It simply has not yet been selected as the specific priority destination during this particular decade. Out of a genuinely crowded field of scientifically compelling, similarly expensive, similarly difficult outer solar system destinations, all drawing from the exact same limited pool of funding, launch opportunities, and radioactive fuel. So here is the honest, complete answer to why NASA has not sent another mission to Pluto, laid out plainly rather than framed as some kind of institutional neglect or lost interest. It is not that scientists have lost interest in Pluto, and it is certainly not that New Horizons failed to generate genuine, lasting scientific excitement about that distant, icy world. A serious, fully engineered follow-up mission already exists, designed by researchers who worked directly on the original flyby, carrying 11 scientific instruments specifically built to answer the biggest remaining questions New Horizons left open. What stands between that detailed proposal and an actual launch is a combination of genuinely difficult, unavoidable physical realities, a journey so long that entire scientific careers would begin and largely end before the spacecraft ever arrived, a supply of essential nuclear fuel that remains tightly constrained and hotly contested across multiple competing missions, and a formal, rigorous prioritization process that, for this particular decade, judged an unexplored world like Uranus to represent a slightly higher immediate scientific priority than a long-awaited return trip to a world humanity has already visited once. There is one more factor worth addressing, honestly, precisely because it comes up so often in public conversation about Pluto, even though its actual influence on NASA's funding decisions is genuinely difficult to measure. In 2006, the International Astronomical Union voted to reclassify Pluto from a planet into a new category called a dwarf planet, a decision that remains genuinely contested among planetary scientists to this day, with researchers including Alan Stern himself publicly arguing the reclassification was poorly reasoned and should be reversed. Whatever one makes of that ongoing scientific debate, it is worth being clear that NASA's decadal survey process, the formal mechanism that actually decides which missions receive priority funding, evaluates proposals based on their specific scientific merit, not on whichever textbook category a given world happens to be assigned. Persephone was evaluated and ultimately not selected for this particular decade, using the same rigorous scientific criteria applied to every other competing proposal. And the researchers on that review panel were entirely capable of recognizing Pluto's scientific value independent of its planetary status. Still, it is fair to acknowledge that Pluto's reclassification has shaped public perception in ways that occasionally bleed into broader conversations about funding priorities. Even if the technical review process itself operates independently of that debate, it is also worth ending on a genuinely hopeful note, because the specific obstacles standing in the way of a Pluto mission today are not necessarily permanent. NASA has continued investing in advanced propulsion research, including more efficient radioisotope electric propulsion systems, the same general technology Persephone's own mission concept depends on, and continued improvements in this area could meaningfully shorten the multi-decade travel times that currently make a Pluto orbiter such a difficult commitment for any single scientific career. Similarly, continued investment in expanding domestic plutonium-238 production, an effort NASA and the Department of Energy have been slowly building back up since production resumed in 2014 after a 25-year gap, could eventually ease the specific resource constraint that forced Persephone to compete so directly against Uranus, Europa, and Titan for the same limited fuel supply. Neither of these developments would happen quickly, and neither is guaranteed. But they represent exactly the kind of gradual, unglamorous technical progress that, over enough time, has a genuine track record of eventually unlocking missions that once seemed completely out of reach. In exactly the same way, decades of patient advocacy and technical refinement eventually turned a canceled, over-budget concept called Pluto Kuiper Express into the mission that became New Horizons. Pluto has not been forgotten. It is waiting patiently the way it always has, 3.7 billion miles from the sun, for the specific combination of funding, political will, plutonium supply, and orbital timing that would finally allow a mission like Persephone to actually leave the ground. When that combination eventually arrives, whether in this coming decade or the one after it, the mission concept is already sitting there, fully designed and ready, needing only the decision to actually build it and the patience, spanning multiple human generations, to eventually watch it arrive. If you want to know the moment NASA finally commits to sending humanity back to Pluto, subscribe and turn on notifications, because when that decision finally happens, it will be one of the longest journeys any spacecraft has ever undertaken, and it deserves to be followed from the very first day.